recording. Are you okay with the recording, David?
Sure. No problem.
All right.
So hello, everyone. I will be presenting 3 examples of using computational multiphysics to model heat transfer in power cables. So what you see here on the screen is a trefoil power cable heated in air, and the heat is being transferred into the ambient environment, which the boundaries extend to infinity. So these boundaries, we look on the left side, model builder. On the component, we expand the definitions, artificial domains. This is something we add to this definition. So you right click, infinite element domain, and then here we define which boundaries we want to extend to infinity. So this is a cable in air that's infinite. Okay, so we need to do different things to set up the model, right? So starting from the top, we have parameters that we define. So typically I have a parameter list for time, parameters for like the total simulation time step, which this is the time step of the values shown at the output, not the time step the software is taken to solve the model. This is just like I want data points to show results, right? And then I have other parameters for temperature. So we need to define an ambient temperature. I use a parameter, right? 40 degrees Celsius converted to Kelvin. Same thing for 90 degrees or any other temperature that you're going to use. I define it. A parameter for the dimensions of the model, just the general dimensions, right? Because I have a general dimensions and I also have dimensions specifically for the cable, right? In this case, it's only one cable. So it's one list, but if I have multiple cables, I got separate parameters.
Let me interrupt you for a second, David.
Yeah.
As you can see here, David has defined the parameters for everything. So that gives him great flexibility. It takes longer time to set up the case, but eventually, which we save when I say he saves a lot of time by putting all this, because then he can change it to any other cable that comes in mind. So if you have a smaller cable, a bigger cable or something, it's relatively easy to adjust this thing. So rather than building a fixed model, I recommend that you build a model based on parameters.
Exactly. So it's adaptive. So we have a new cable, different dimensions. You know, the same cable type with different dimensions is very easy to modify the dimensions and just build it automatic. Is like Professor DeLeon says, is it time efficient, saves time. However, because I'm doing like modifications with the cables contacting each other, and I'm creating these boundaries for the domains near the triangle region where the cables join. Sometimes these operations get undefined and we need to redefine them, but that's a quick fix. It is much quicker compared to if we did not have a parameterized model. So if that happens, just quickly go through the geometry, see what's the error, and just redefine it, and that takes care of that. Because like we mentioned in the last class, that in the region here, where the cables come in contact, if we don't put effort to create and control the geometry here in this region, then the mesh will degenerate mesh elements with very low quality, and that could cause divergence of the solution or inaccurate results. But most likely, not inaccurate results. Most likely, it's just going to be a convergence problem. So you want to minimize that. So once we have all the parameters, defined, I have different categories: geometry, electrical parameters for frequency. So I have general parameters, frequency, some electrical conductivities, resistivity stuff, values, right? And then I have specific cable parameters. So in this case, I use the IEC equations to calculate the losses in the cable. in the conductor, skin effect, proximity effect, and losses in the sheet. And I set the thermal limit to the conductor to get the value that's expected for the loss, right? But also at the same time, I'm also in the definitions, I'm applying probes to all the important boundaries that I want to monitor that's relevant and important for the design, right? So for capacity calculations, we are concerned, very high priorities to ensure that the boundary of the conductor does not exceed the thermal limit, which in many cases is 90 degrees Celsius. So I apply temperature probe to all the conductor boundaries, and also apply probes to, like for example, the sheet. In this case, that's the sheet of, and I got different phases, right? So for all the phases, I do the same thing. So phase A, B, C.
Let me interrupt you again,
Yeah.
because most people here are transformer people. So the condition is the same for let's say for a large power transformer, you still need to put whatever is the thermal insulation or the maximum temperature at which your insulation performs. You would still put it in the conductor, let's say 90 degrees. If you're using a transformer that is class F, I think, that has the 90 degrees temperature, operation temperature at the conductor. So these things are the same. If it is a cable of a transformer, these things can be extrapolated easily. Continue, please.
Yeah, so everything that we apply for the power cable transfers to a transformer model, right? Because at the end, the transformer has a winding, which consists of conductors, right? We have insulation, so those conductors are heat sources. So everything transfers. So once we apply the probes to all the elements and boundaries that we want to monitor, we can see the results live as the simulation is running. We can see those values, and if we see something doesn't make sense, we can stop the simulation before letting the simulation run for whatever time it takes to finish, right? We could immediately, detect something's wrong. We can stop it, fix it, and then continue. And then once we see that things look good, then we let the simulation run. We let it finish. And then we could also apply probes for pressure. I can show you here all the different variables that we can monitor. So if we click this drop down here, this menu pops up. We could see variables in heat transfer and solvent fluids. So we could see heat fluxes. We could see surface radiation variables. We could see laminar flow variables if you want to see velocity, pressure. So we have control of all the physics and model, and we get a set of probes to monitor these values as the simulations run. So what I do is with the temperature variable, I use this variable, I give it a name. For example, conductor temperature phase A, and then over here, variables. I'll see it's still under definitions. I have a variable called 1A. This is phase A of conductor 1. And I'm using that, well, actually, not in this case, because in this case, I was doing something else. But let's say phase B. Phase B, I have the variable that I'm probing from, right? So the probe is measuring the temperature of phase B, and I'm using that variable to compute the DC resistance of that phase, right? So as the simulation is running, temperature is going to increase, right? As the heat source is applied, temperature is going to increase. That's going to increase the resistance of DC resistance. I use IEC equations. I could compute the AC resistance, compute the sheet loss, and then here this is my conductor loss computed with the IEC equation. This is the sheet loss computed with the IEC equation, right? So these are variables that are changing with time as the simulation is running. And these variables for the heat source, I'm applying it over here. So I compute all the heat sources, I apply it under the heat transfer in solids physics, heat transfer in solids and fluids physics. And also I need to define temperature for the boundary. In this case, this is open air. So basically the temperature is the same all around the boundary, which extends to infinity, in this case, 40 degrees Celsius. So this is the boundary that extends to infinity. This boundary is fixed at this position. We don't see, we don't visually see the boundary extend to infinity, but it's a mathematical operation that the program does. And then for surface radiation, we need to define the radiation boundaries. In this case, it's only the cable surfaces. And we define the opaque surfaces, right? The solid objects that the boundaries are on, in this case, the cable jacket. And I do not select any domain that is not participating in the radiation. Only domains that have the boundaries participating in radiation are selected. So in this case, this domain here, these domains here, where the cables connect, where they're in contact, there is no radiation taking place. This is purely conduction. So heat transfer, there are three modes of heat transfer: conduction, convection, radiation. So in the conductor, everything here is all solid material. So we have the conductor, insulation, conductor screens, sheet, all solid. This is heat being generated in the conductor and the sheet and dielectric, and that heat generated within the cable is being transferred out of the cable through the jacket, and from the jacket is transferring radiatively by surface radiation for surface between cable surfaces, and also to the environment. Is radiating heat to the environment. So over here we define ambient temperature, right? So we define the temperature in the model for the ambient, and did that solve for the radiation heat transfer. Also, we define under surface radiation, we define the fluid, what is transparent, right? So in this case, air. So all the air domains are selected. And then last is the laminar flow physics. So we select the fluid domain, and we have these default options here, I should say nodes. So we're modeling natural convection. So we select include gravity. And in this case, gravity is pointing down, negative y direction. So in gravity, we set the gravitational constant, right? Negative pointing down. And then we need to define what is the boundaries where the heat is going to be flowing, right? So in the bottom we have he's going to be rising, right? So in the bottom and the top is open. It's actually open all around, but we know that heat is going to be rising from top to bottom, right? So we have an open boundary in the bottom, open boundary in the top, and for the size, I leave it open for heat to transfer in and out, but I let the solver determine that. So I don't put any restrictions. I just let the heat, let the fluid flow and rise naturally, right? And then I apply a pressure point wherever there's an enclosed domain. I apply a pressure point constraint. And then these are three physics modules, right? Heat transfer, solids, and fluids. We don't really need laminar flow physics, because this physics here has heat transfer in solids and fluids, but we need laminar flow if we want to solve for Navier-Stokes equation. If we want the full solution for natural convection using Navier-Stokes equations, and we want to see the velocity field, we need to use laminar flow. Otherwise, we could solve using fluids, using boundary conditions, right? We could apply a boundary condition on the jacket of the cable. We wouldn't need an air domain, right? We would just need the boundary condition on the cable surface and select the empirical equation for a cylinder, horizontal cylinder. So we could not use laminar flow, just use boundary conditions by knowing and choosing the appropriate heat transfer coefficient for this specific geometry. But then we will not see the velocity field, or it will not solve the full convection physics, right? For like using the Navier-Stokes equation. So one thing I love about COMSOL is this right here. For every physics that we select, we could expand the equation and we could see the equation that's being solved in the model. So this is the heat equation. So we can see the different terms in the heat equation. We can see the equation in surface radiation. We can see the equations used in laminar flow to solve convection. Right? This is Navier-Stokes equation. This is why I love COMSOL. In ANSYS, it does not show you explicitly the details of how the physics is being solved, unless you open the manual and you have to search the manual, right? In COMSOL, you see the equations in the program. You don't. It's not necessary to open up a user manual or user guide or anything like that. So we see here what's going on. So once we have all these physics in place and set up, configured, we need to now also include multi-physics settings. So the surface, we have laminar flow coupled with heat transfer in solids. So that's why we need this non-isothermal flow. This is going to couple laminar flow with heat transfer in solids. And in here, the domains of the fluid is selected. We apply the settings in this physics. In this case, laminar flow, heat transfer in solid fluids. And we could select or unselect any these energy balance options, right? And then similarly, we need to couple the heat transfer with surface radiation with the heat transfer in solids. So we just select heat transfer in solids, surface radiation, and that sets up all the physics. Then, as mentioned last time, we need to mesh the geometry. And I use mesh operations as I explained last time, because I like to have full control of how the geometry is created. Number one, to maintain and obtain high quality mesh, not below a limit. So I want to have like a threshold of the quality, right? And also I want to have control of the boundary layers. I want to control the number of layers. I want to control stretching factor, thickness adjustment factor. I want to control this myself. Sometimes simulation converges good. Sometimes you need to do something to get the convergence to take place, right? So sometimes we need to adjust these values here. And then going to study settings, we went through this last time, right? So I'll just go quickly. So
question here, David.
Yeah.
Why is it that next to the conductor, I have a next to the cable, I have a different mesh that seems to be more refined in the air, that is a little bit far from the cables.
You mean like over here?
Yeah, this part. Why is it that you changed the meshing technique?
Okay, so here is where temperature gradients take place, right? So the conductor surface, it's better to show you with an image, right? So we have this image. This is a solution, right?
So you model in more detail the section, the place where the largest temperature gradient will happen.
Yes, exactly. Yeah. So but that's in general. It's not only temperature. If this was voltage, right? There's a voltage distribution, voltage, diffusion. We need to do the same thing with voltage. Right? If there's a voltage drop, we need to capture the gradients This is a
All
temperature
right.
drop. We need to have a mesh that captures the gradients.
All right. Thank
That's
you.
why that's why I have this. I got 12 layers, and it starts off very steep, right? The slope from the temperature is very high, and then it decays, right? Moving away from the cable. So this is capturing the gradients. So as mentioned last time, in this case, I don't need a ramping function, right? But if I did, let me see if I don't know if I have it, I took it off. But yeah, like here, like I have a ramping function, right? So if it was like typically one cable is no problem. But let's say we have like I'm gonna show you in the next example. I have a tunnel with like 6 cables, and it's sometimes in that case, in my experience, it's been very hard to get the simulation to starting and to converge without using a ramp function, right? In this case, I don't use it. I just control the time stepping, initial time step, and everything works fine. It converges easy, and I define the relative tolerance. I always aim for a minimum, or I should say maximum, right? 0.00004. So 10 to the negative 4. So I run this, I get the solution, everything's good. Now, in this model, any model, we could select show maximum and minimum values, right? If I'm running, when I'm running the simulation, like I said, I could see the results like being solved at each time step, right? I know I applied a boundary of 40 degrees Celsius, right? As soon as I see that the minimum temperature is less than my boundary condition, because the boundary is supposed to be the lowest temperature, right? But if I see that I'm measuring a temperature that's lower than my minimum, right? Then that's a problem. Then I would stop the simulation, and I would, in that case, perhaps it's the airbox size needs to be bigger, or this infinite domain thickness needs to be bigger. Something needs to change and increase the mesh density, but this right here is showing that it's not respecting my boundary condition, right? Because that boundary condition needs to be respected. But that's in general. In any FEM software, you it's not just one airbox, or should I say model domain, right? It's not one size fits all, right? This whatever you want to call it, simulation domain, model domain. In this case, is the airbox, right? So in this case, I would ensure that this minimum temperature is not less than my boundary of 40 degrees. So in that case, it's just, yeah, I got a question?
No,
Okay.
no, but well, I do, but it's 39.8. For me, those are 40. So why is it so complete? Why so
I
concerned?
mean, it's true. From my experience, this doesn't change the results, because when I do fix the model and I ensure it's 40 degrees and I compare with a solution like this, it's the same. But just to be extra safe, right? I myself, I like all my models that all the results are respected and there's nothing being violated. It's not really
Okay.
critical, but that's just the way I work. I like, because it
Yeah, and
doesn't.
I understand. I understand. It's pointing to some imprecision of some sort.
Yeah, exactly. So it doesn't have to be like
Bec-
this, because I can always
Yeah,
fix it.
because
Yeah,
there are boundaries that need to be respected, and
exactly. Yeah, I mean,
yeah. All right, fine.
so because look maybe like if I'm doing like a lot of testing, right? Maybe I could just leave it like this, right? But once I'm trying to obtain the final result and I'm gonna deliver to a customer, then I'm not gonna leave it like this. I want to make it right. If it's just for myself, I don't care about this. I'll leave it like this. But if I'm gonna give it to a customer, okay, I gotta make sure everything's.
Yeah, I was gonna say you come with paint and erase the bottom temperature.
Okay, so that's this model, cables and air. So let me see. I show another example. See, stop share. Okay, I got the cable in the tunnel. Now this is similar. Like the setup is basically the same thing I explained cables in air, the same setup, except for a cable in soil, we only have one heat transfer mode, which is conductive heat transfer, right? There's no radiative heat transfer. There's no convective heat transfer. Everything is just in soil. Heat is generated in the cable.
Is that a three-core cable with fillers?
Yeah, yeah.
Okay, so it's only solid. The whole thing is solid.
The whole thing is solid. Fillers, yeah, exactly. Solid filler. So heat's generated in the conductor. And if there's dielectric loss, we apply dielectric loss. But all that heat is going to transfer out of the cable. And that heat source produces a temperature distribution, right? And all that heat transfers to the environment. So in this case, different than cables in air, I'm only applying the ambient temperature to the top boundary, right? Because the top boundary, that's the boundary between soil and air. So that boundary is the ambient temperature, whatever it is. 20 degrees, 40 degrees, whatever. And
Question here, please. Question.
David,
yeah,
yeah, if your cable is buried under earth, so or it's in a tunnel, so your heat should be dissipated in all directions, right? It shouldn't be in the upper direction only.
no, it is being dissipated in all directions,
Yeah.
but the temperature is fixed on top. The top is isothermal. The temperature in all directions, in the sides and bottom, they're gonna vary. Whatever temperature is gonna be, right? The solver determines that. So if I
Show me, please, the temperature distribution, and if you have the isotherms,
yeah, like this, yeah.
And
See,
instead of the
going
heat
to the
flow-
side, yeah.
remove the arrows and give me the isotherms if you can, please. I can explain this.
But this is in right?
This is in solid, in ground. It's an underground cable. So the air starts here. Here is air. The rest is the ground.
Yeah.
And it's buried about a meter underground, which is the standard, about a meter. I think it's 3 feet, which is 91.
Let me see what I'm doing.
No. You put the convective.
Oh, it was the lines, right? Yeah, my bad.
I went the lines.
Yes. So we need
Yeah, this is good.
Console, yeah, console.
Just put the lines because the lines will tell me more than only the color distribution. Put the lines, the isotherms. There you go. This is really how the heat is dissipated. As you can see, going up, the gradients are closer. So because from here to here, the heat in the end will dissipate this way, but it diffuses ground down to the ground. If you remember, the explanation of diffusion is come with a bucket, throw it in here in the carpet, and it has expands like this, diffuses, but it has a maximum reach. It doesn't go to infinity. It goes to infinity in an exponential way, e to the minus something. But you know that after 5 tau, 5 time constants, it doesn't matter. So as you can see, this one, the first isotherm over here, which is probably 35 or 36 degrees, is going to have a circle that is almost infinity.
Boundary was 40 centigrade, I guess. But now it's just 35.
Well, that's what he says, that he didn't like it.
What happened?
No, it's because Fayaz is saying that your isotherms are saying 35 degrees, but your ambient was 40. So how come? What is happening? Something is cooling. And then I told
No. Remember, that you're talking about cables in air was 40 degrees. This is a different model. This is soil, 35 degrees. I'm using
35.
thermal. See,
I see. Yes, thank you.
35 ambient, 35 degrees.
Fayaz misled me.
No, because this cable.
It's all Fayaz's fault.
All right, but this
No.
cable. Wait,
Yeah, you're right. So this 35, not 40. So it's okay.
Yeah, this
From
cable.
From here to here, there is only 0.5 degrees. Now, zoom into the cable, please. So in here, you can see that there is a lot more, the temperature is changing a lot more in these layers, right? The conductor is at 90, but most probably the jacket is already at 80, right? 88, 70 or 9 or something. So it drops very quickly here. And then it's slow, the temperature variation. And not only that, it's not only in this way. If you look at it in time, it will be very slow. It will take years to actually get to this thing.
So you want to see the plot? This
Okay, this is the plot. So this
years.
is in
So
years.
after 1 year, we pass the knee, and then it starts to go steady state. So we need at least a year.
Can you show the first 2 years? Can you cut this plot to 2 years?
Yeah. Let me see. Oh, so this is two. Yeah, because it's very steep. I mean, when we do 1 year, maybe you want to
No,
see.
but go all the way. Don't cut it in 50, leave it at 90. The white.
Okay, yeah.
There you go. So it's very steep at the beginning. This is a conductive temperature, right? And,
Yeah.
and then eventually it goes slowly. So after, I don't know, half a year, you can say, well, it's almost there. All right.
Yeah. So this is
If you are
cable.
deeper, it will take much longer. If you are 10 meters deep, it's going to take
Yeah, the
10,
deeper,
20 years.
more mass, more soil mass to store heat. So it takes longer for the conductive temperature to rise.
All right.
So that's this example. Now, the reason why 35 degrees, the ambient, because this cable, I use a manufacturer data sheet for a cable in Saudi Arabia, and they specify 35 degrees ambient temperature. So it all depends on the location where the cable is being installed, right? Different parts of the world, they use different ambient temperatures. So that's what determines that. Okay, let me see the next example.
I'm sorry, I have a question for this.
The soil example?
Yes.
Yeah, what is it?
It's more like a general question about the your cable setup. You have several lines between the cables, so you're just trying to make the cable contact in a surface, not a circle, right?
You mean these lines here?
Yeah, like between the faces, like connecting the conductors.
Oh, like here.
Yeah.
Yeah, exactly. That's just I'm chopping up the geometry so that I can have this triangle, right? And that could be meshed.
Okay.
So
And
the reason, see how, is because if you want to model all the way to the point where the cables make contact, at those points you're going to have degenerate triangles,
Yes.
and that is going to give you convergence problems to the point that the program is not going to converge.
Yes.
Now, physically speaking, it's like two bodies don't touch each other at a point. They always deform a little bit,
Yes.
right? They
Yeah.
crush each other, and then there is a surface, not a point of contact.
Okay. Yeah.
and it is more critical if the model, if there's fluid in between the cables, right? If this was fluid and I want to apply a boundary layer, that's gonna make the quality even lower. But
Yes.
because this is a cable in soil, no fluid, I just have to mesh. I don't have to put a boundary layer. So
Okay.
this quality would, in other words, in purely conductive model, right? No convection, the mesh is always better in a purely conductive model. Because once we involve convective heat transfer, fluid flow, and we have boundary layers, those boundary layers always reduce the quality a little bit to some extent.
And one more question. So the blue triangle you're showing right now. So so you try to make the mesh better. So what's the angle so you're choosing like here? So at the point, did you like calculate the angle like intentionally to make sure that the mesh is better?
Not exactly, just like this. See this line here?
Yeah.
This line. I just rotate it. I use this like this. I use a horizontal line like a reference, and I rotate this line to go up to be here,
Uh-huh.
and another line in the other direction, right? Just
Okay.
to have a point of contact, so I could create a line to connect, but not.
At this point, heat transfer.
It's just
Yeah.
you know like just by eye. I just look by eye to see if it looks good. Okay, I try it out. But that's adjustable. That's a variable. So I just in over here geometry.
Okay.
I
Yeah.
don't know which one it is. Like for example, like rotate. See, I just put the angle, right?
Yeah.
And I check to see how it looks. If it passed, looks good to me. I check the mesh quality. If it's good enough, I keep it. If it's something I need to adjust, and I adjust it here somewhere. I forgot. I don't know where exactly it is, but
Will that be the equivalent?
I mean, you could spend more time to do like a set it up mathematically to be exactly right.
Yeah. So no, I was
Well,
asking, do you
equilateral triangles are better, but you cannot always get them, right?
yeah.
Oh,
I get it.
exactly. Yeah, that's true. Yeah.
Okay.
Yeah.
So that's a pointy the this triangle like pointing down that angle. You just you didn't like calculate like the
No, I
back,
didn't calculate.
right?
No.
Okay.
I just rotate the line,
Okay.
the radial line. That's it. And
Okay.
then I connect the 2 points.
Okay. I thought there's some like intentionally technique. Okay. Okay.
Now,
Thank
what I'm trying to say is like, now,
No,
you
but
see,
this
this
is
is
based
one
on
domain.
experience.
That's like the bottom line is this is one domain, right?
Yes. Yeah.
I create this line,
Yeah.
and I join them with this line, right?
Okay. Yeah.
But this is one domain. Even though when I build a mesh, it looks like different domains, right? But it's not.
Yeah.
One.
I get it. Yeah. Okay. Thank you so much. Yeah.
All right, no problem. All right. So then I gotta go to the next model then. So I gotta go the tunnel. So this now is a tunnel with 6 cables arranged symmetrically, right? So on the left side, we have a small cable, medium size, and a large size, right? Reflected along the vertical axis, having this showing the same cables on the right side, right? Just symmetry, reflection. So I got 6 cables. Each cable is a trefoil, right? So I got 3 times 6, 18 single core conductors. So I need to monitor 16. So I got equations and probes for each single cable, right? But everything else, everything I mentioned in the previous examples, everything carries over. But now we're combining. Remember, the first model was cables and air. The second example was cables and soil. And this is a combination of both, right? Because in the tunnel is air, right? This is air. And then outside is a solid, this is soil, all around is soil, right? This is concrete. So we have convection and surface radiation between the cable jackets and the tunnel wall, right? So heat is generated in the cable and it's transferring out of the cable jacket, transferring out by way of surface radiation and natural convection. And then you see, so the final solution is like this. And in this case, I was modeling the soil to have different thermal conductivities. So the bottom domain has different thermal conductivity than the top layer, and then one above that, and the one above that, all different properties, right? But everything else, as I mentioned, is the same setup. So we set up No, once we have the equations for the heat sources, right? Then we apply those variable heat sources to each domain, the conductor, dielectric, the sheet, right? We have all the heat sources. We apply the boundary condition. And this example, I show it applied to all the boundaries, but really I'm gonna apply it only to the top. So this is just like this is an old model, right? This experiment. So once we have the boundary condition, we also have the infinite domains as before, right? So the left, bottom, and right side extend to infinity, and the top is fixed because that's the surface, that's the boundary between the soil and the air, right? Environment. So we set up the heat transfer in solids, we set up surface radiation. In this case now, it's not cables in air, it's cables in air in a tunnel. So we also need to include in radiation the boundaries of the tunnel wall, right? Concrete wall. Again, we have the opaque boundaries, which is only the domains participating in the radiation. We have the fluid for the transparent domains. Same thing, laminar flow, everything I mentioned is the same thing, except here there's no open boundary. So remember cables in air, we had the air box, top boundary, bottom boundary was open. In this case, nothing's open, everything's closed. All we need is to select gravity. We can check use reduced pressure typically when we have fluid that's enclosed, like in this case, right? We have air in the tunnel, the air is enclosed, so we could select reduced pressure. This would help, in some cases, help with convergence. We select all the domains that are enclosed. So in between the trefoils, we have trapped air. So we select the pressure point constraint. And I select one point anywhere in the exterior domain of air that's bounded by the tunnel wall, right? So I select the point there. And we need to define our reference. Yeah.
Pressure point constraint. Can you please repeat the pressure point constraint thing?
So wherever there's air enclosed, I select a point, applying a pressure point constraint. So apply a zero, in this case, zero pressure, 0 Pascal, right? So in this region, that is really not much air moving, first of all, right? In this domain, because in this region, the temperature is pretty much uniform and the air is trapped. So it's really not air moving, right? So really, this region is not really important, right? But it's important for convergence. That's my point. It's not really important for affecting the solution, the final result, but it's important because it's part of the model. It affects convergence. So we need to manage this.
Yeah. My understanding, David, is that if you don't put the pressure point, it will not converge, right?
Exactly, yeah.
So basically, it's a trick to make it converge. But this is clear from the console manual and things.
Yeah.
But David, in practical, there is a, I think, small gap when we do the what we call it, this configuration of cables, trefoil. So
Yeah, that's the gap. That's the gap.
There is a gap.
Zoom into the dead triangle, David, please.
The gap?
Yeah. So, and that gap, it exists, but it's very small. Air doesn't get to move. The radiation doesn't change much because the temperature of the surfaces is about the same.
Exactly, yeah.
They
the
are
cables
on,
are touching.
the cables are touching, so the conduction goes through that.
But in practical, cables doesn't touch it.
No, they can touch. In this case, this is the oops. So the cables are touching here, right here,
Yes.
but they are not touching in this other part.
So what that means is like in real life, you may have a gap
Yes.
between the cables, like they are not touching completely something.
Well, yes, but that you can also model. Yeah.
But if we model that, then there will be some air gap, right?
There will be some error gap.
But this is even more conservative than that. So
Mhm.
So he is not simulating the deformation due to heat.
Deformation due to heat is not being simulated, no. But you
David,
can see here, the temperature, very good. The temperature everywhere there is about the same.
Yeah, so this is what I'm trying to say, like.
So nothing
here-
moves, nothing radiates. You can
Yeah.
eliminate it. But if you don't, if you eliminate it, if you don't model it correctly, it will not converge.
Exactly. So we see here, the minimum is 89.5 and the maximum is 90. So it's only a half degree difference.
Yeah.
Not,
Now,
it's not a significant.
Honestly, you can just make that plastic or PVC or whatever the material.
No, yeah, we could also in laminar
Yeah.
flow, we could just not select it. Just
Yeah.
don't make it part of the model,
Uh-huh.
but it's
one
not
question,
here.
Professor David. Can you
Professor
hear me?
David, answer
go ahead.
please.
Yes, one question. The heat source is only in the core of the conductors. Are you considering or have you simulate the case where you have heat also in the shielding?
Yes, this is model.
It is
So-
considered.
Yeah, so here, look, conductor, let me see. That's conductor,
Mhm.
dielectric.
We consider
That's
dielectric
the
losses
sheet.
too.
Yeah,
Oh,
so we have three. We
oh,
have the
okay.
sheet.
So it's the conductor losses, the dielectric losses, and the
The
sheet
electric
losses.
losses and here, okay.
Yeah.
Everything is computed in the variables for the cable using IEC equation, right? So here,
Mhm.
TC1A, this is temperature of the conductor, cable 1, phase A, TC1A. That TC1A is right here in my probe. Think of this like a laboratory, or like you have, if you're a billionaire, right? You could afford the best technology. You could put sensors anywhere in the cable. We have probes that monitor every single boundary, every single point, every single domain, and we use that in the equations. Right? So we have the temperature to update the DC resistance of this conductor. Then we use the IC equations. We compute the parameters to compute the skin effect, proximity effect, right? To compute the AC resistance of the conductor, right? AC resistance of the conductor depends on the DC resistance, which depends on the temperature, right, of the conductor. And then we use the other equations to compute the losses in the sheath. In this case, I believe it's single point bonded, but you could use any bonding method, right? So once I calculate the alpha, then I compute conductor loss, and the sheath loss is a fraction, right, of the conductor loss, right? The A11 is that fraction, right?
Let me explain a little bit things here. I don't know, Fermin, if you are familiar with the IEC calculation methods for cable ampacity.
No, I know we have
No?
to solve some problems, but only consider the heat source as in the core.
Yes, so
I can see that you consider.
the IEC standard 6286 series give you equations to compute the heat sources, the ampacity of the whole thing,
Okay.
with all heat sources considering all inductances, all mutual heating, all eddy currents between a circuit. There is no eddy currents from one circuit to the other in the ampacity standard calculations. So when David has here 6 cables, so the magnetic fields or the electromagnetic fields are constrained to the circuit, right?
Yeah.
So only the eddy currents, proximity, and skin effect are only considered per circuit. The IEC doesn't have the equations to consider the induced electromagnetic fields from one circuit to another.
Okay.
Yeah. But
So you didn't have to solve the electromagnetic problem first.
you don't need to solve the electromagnetics
Okay.
if you go this way. Now,
With this way.
if you want to model the entire thing multi-physics, and you're willing to pay the price for the time that it's going to take, certainly you can.
Okay.
I mean, David has built some unbelievably complex models for generators. You have a 3D generator with screw windings. It's been really crazy. I don't know if you still remember those models, David, but
Yeah.
so
Yeah,
we follow
so
the standards. And the reason is because this work was done for a power utility. And
Okay.
the power utility always want to use the standards.
Mhm.
So utilities want to do the standards, so we use the standards. And the job is a lot cheaper if we use the standards for the calculation of losses than if we do a multi-physics calculation. Because now, if you're going to go eddy currents and all these things, your meshing needs to be very fine for to allow the eddy currents to be properly modeled in the solids.
Okay.
Yeah.
Yeah, I
And
understand.
still because the cables are stranded, you're not going to put a stranded cable here.
Mhm.
It is going to just kill your simulation.
no, not necessarily.
Yeah. So we do multi-physics, but with a single physics, we approximate as much as we can.
Yeah, look, the bottom line is we need a heat source. We
Mhm.
either use equations to compute the heat source, or we just apply the heat source, just put a value, right? No,
Uh-huh.
if you know it, you just use it. Or we have to add an additional physics. We add an electromagnetic physics to compute the electromagnetic losses, right? The electric loss to compute the Joule losses in the conductor and in the sheet, etc. Right? But in
Yeah,
this case, we're using equations. But if we have to, if there's a loss that we need to consider that's not in any standard, then we have to use the Joule heating solver or the electromagnetic solver, then we do it.
Exactly, you're going to do.
But okay, see here, this is again an advantage of COMSOL multiphysics, because everything I explain here, like using probes,
Mhm.
right? Probing the conductor boundary, right? We do this easily in COMSOL multiphysics. Everything in one program, one platform, right? If you want to
Now-
do this with ANSYS, you need
Yeah. And now let me put a qualification on this. David worked for ANSYS. So if he's telling you use COMSOL, he knows what he's saying.
It's good.
No, I'm being honest. Like I worked with ANSYS for like a year and a half. I already had experience with COMSOL going in working for them, right? So I already knew what COMSOL could do, and I was asking them if ANSYS could do like similar things. So if you just use ANSYS Maxwell by itself, ANSYS Maxwell by itself does not have any probes to measure any quantities as the simulation is running. We cannot use the variables as I use it here. The only variables available in ANSYS Maxwell are basically parameters. They're not even like real variables, just parameters.
Yeah, but the way to do it is you pre-compute the loss with the magnet or whatever is the version of ANSYS. You pre-compute the loss and then you just import it here. But
Yeah,
of course,
the bottom line is not the same. You have to do, there's another workflow. So whether you
you have to do more
pre-compute it,
work. Yes.
yeah,
Yes.
more work is you have to pre-compute it, or you have to set up two models. You have the electromagnetics model, and then you're gonna have the ANSYS fluid, like fluid flow model, heat transfer model, and then you need another model to integrate both of them. It's called
Yeah.
workbench. So anyway, it's very complicated. Anyway, that's why I like quantum physics, because everything is one program. We have probes for everything. We have complete control. This is for innovation, right? So everything I explained is basically the same. Like look from the top: parameters, variables, probes. Once we have that, heat transfer solids and fluids, right? Apply the heat sources. I got a lot of cables, a lot of right, it's a lot of single cores. So I had 18 single core cables, and each single core has 3 types of laws, right? Conductor laws, dielectric laws, sheet laws. So that's 3 times 18. So I got a bunch of sources to manage. Same thing, surface variation, laminar flow, multi-physics, coupling, and that's it. Run the simulation. But okay, I mentioned before that it's not always necessary to use a ramping function. But in this case, I got all these cables that need to initiate and start. And because they start at the same time, they have different requirements to satisfy the initial condition, right? You know, the way the solver is going to solve it, the cables got different positions and different locations. So it's very hard to start the simulation without a ramp function. Like if we just put the full load of the initial heat, it's going to be very hard to convert it. So I use this ramp function. So I say, and it looks like this. So the initial value of the heat source is 0, right? So just consider initial temperature and then reach the full load after 15 time steps. So after 15 time steps, know that the heat source is ramping slowly, and then once 15 time steps is reached, then the full load is applied. So then I get
Is it a transient simulation?
This is a transient simulation, yes.
Fine.
Yeah.
Around function.
Yeah, the purpose is, the reason is because I'm positive. Go back to the previous figure, please. It's something important I need to explain here.
which one?
The temperature rise.
The exponential
The-
saturation.
No,
This one?
that one. Yeah, but I don't want to see all that. Okay, very good. As you see here, the temperature here, the temperature is rising, but the very slowly, because this is a deep. How deep is this tunnel?
20 meters, I believe.
20 meters deep. So the time constant takes 40 years, not even. It takes 200 years to get to steady state. So because cables are specified to last for 40 years, companies cannot say, oh, what is my ampacity in steady state? Because the engineers who install it are not going to be alive 200 years later. So no human lives 200 years. So and working time is about 40 years. So that's why we designed it for 40 years. If it fails after that, who cares? I'm dead, right? So so cable need to be rated for 40 years. So that's why we need to do the transient to know what is going to happen at 40 years. So at 40 years, these cables are going to exceed by maybe 1 or 2 degrees. So it's up to the engineer in there to say, well, yes or no, or reduce the current or do something. But cables in tunnels are always rated for a transient. Always.
Yeah, and that's all, folks.
David, you have any other example?
I just got, I mean, these 3 covers
Can you
basically
show
everything.
a 3D, the 3D,
Oh, the force
Right.
ventilation?
the tray? No, the 3D tray.
You mean the trough, the ventilation, right? The
No,
project?
not the trough, the tray.
Oh, the cable tray. You mean
Yes.
the transformer one?
There was one 3D model that you had. It wasn't the trough, right? It was a tray.
But the tray, you mean I think the trough. Is that the project?
Maybe the trough, yes. I don't remember which one.
The force ventilation and the turbulent flow?
I guess so, yes. If you have it available, if not, then
Let me see. Wait, let me have to find it.
it's okay if you don't find it. It doesn't matter. I think you're giving us a very nice introduction to this.
That's the RTE trough, right? That's the way you're talking
The
about?
RTE trough, yes.
Yeah, I got it. Hold on.
Yeah.
You sure?
Yeah.
I'm wearing the same shirt. That's the one I wore yesterday.
Oh, I got it, yeah.
All right. Very
Share
good.
screen.
Yeah, because I seen very interesting things in there, so
You see your screen?
it's coming. Yes.
It's a big model, so it takes time to load the results.
So what this is a like a mini tunnel that which we call a trough that goes under a meter or 2 meters, and then air is not being blown through the surface. It's not being blown through the entrance to the end, but there is some air circulating because of pressure difference. So there is a high difference between the entrance of this trough and the exhaust. So air flows naturally by natural convection, by pressure difference from in to out at about 1 meter per second in the steady state. That's what that we measure. But of course, it becomes not uniform at some point. So at the beginning, if you look at the beginning,
Well, the entrance is right here.
the entrance, the air is not only laminar, is the same speed at every point.
Uniform, yeah.
Yes. Now, as you move into the tunnel, at some point you're going to get you see that there is a different distribution. So the air is gaining speed as you go into the tunnel, and then at the middle or whatever we call the fully developed flow.
Yeah, right here.
The fully developed flow is when when you reach, let's say, the steady state of the flow.
Yeah. So yeah, exactly. At the fully developed region, we
It's
have
that shape that you see. Yeah.
A steady state of flow of the fluid, a steady state velocity field, and that pretty much we have different slices to verify this, right? So this slice, I got different slices showing that it is changing slowly, right? But not as much. But as we get closer to the exit, it does increase. It does change a lot.
Mhm.
But at the exit is where the fluid flows the maximum.
Yeah, and all this flow because of the speed is, I think it's still laminar, right?
I
don't
believe the
remember.
model was turbulent.
Okay.
Yeah, we use a turbulent model.
Okay. So,
So yeah, one thing to mention.
is it what are the complications on modeling this? Different from other things that what you have shown? What would be a complication or a particularity that somebody will need to know to do this?
Yeah, okay, so this is 3D model. So the large project, large file. In this case, we take advantage of symmetry, right? So the symmetry along the YZ plane, right? So we cut it in half, and that's going to reduce the size, right? By at least half. And then also, I forgot the full length of the project, but so in this case, I'm modeling, I think 50 meters, right? And the customer, I think, wanted like 300 meters. It's not necessary to model 300 meters because we know the fully developed region is less than that, right? So we need at least the fully developed region and like extra length, but not much more than this. Like 50 meters was sufficient, right? So what we need to do is we need to not only mesh. Let me show you the mesh. So it's not only mesh like a face, right? Like 2D. Now we need to mesh along the axis of the fluid flow, right? So we need to first, very important, mesh the fully developed region by a few slices. And then after where the fluid flow is like changing less, then we don't need to have as many slices in between. Really, what I should have done is I should have also sliced at the end of the tunnel. I mean, where the fluid exits, I should have chopped it a little bit, but we already saw that there wasn't much variation. But wherever that we see there is a lot of variation, like a lot of gradients and stuff like that, we need to have a high density mesh. So what I do is I don't let council mesh this for me, because if we let council mesh this for us, it's gonna do an attempt. It's gonna do its best, but you lose the control. I like to have control. I like to determine and say, okay, I want these many slices. I want the fully developed region to be divided by these many slices, right? I control exactly how many slices to chop up the region. I could do that by the fully developed region. I could do that by the exit. I control how and where to slice the mesh. And what I do is a sweep. So first I mesh only the front face, and then I sweep going along the z-axis. And at the end, that gives me the best quality mesh. But everything else is pretty much the same. But okay, once we apply the boundary, the symmetry condition, right? We need to apply the symmetry boundary. So that's the symmetry plane. So we need to add a symmetry node in the physics. And we need to do this for every physics, right? We have 3 physics, heat transfer and solid fluids. We had a symmetry node, select the boundaries of the symmetry plane. Like the same thing with surface radiation. We had a symmetry node, and the same thing for fluid. In this case, the fluid is we only selecting the boundaries of the fluid. Right? In each case, in each symmetry node, we only select the boundaries that's relevant to that physics, right? Because in this case, the solid boundaries is not relevant to the fluid physics. And everything else is pretty much the same. So once we configure these extra settings, we run the simulation, but you need to know your fluid flow regime. Do not assume it's laminar when it could be turbulent, right? Because if it's turbulent and you try to use a laminar flow solver, you're gonna have problem. If you use the correct solver, you're gonna get better. You're gonna get convergence quicker, and you're gonna get the accurate results. So there's equations to compute and look at, analyze to know which.
All right, there we go. So I got it all squared away.
What was that?
I'm sorry.
That was Sihao who is talking to somebody.
Okay. I mean, that's it. Any questions?
No, this is
I'm sorry. I have this question. So for your 3D model, is it still in the time domain?
Yes, I do everything time domain.
But
Wait. I typically do, and let me see. In this case, probably not. No, in this case, stationary.
yeah. So let me talk about that first.
Yeah.
Years ago, let's say 16, 15 years ago, we tried to do stationary simulations, heat transfer simulations, stationary, and COMSOL told us that they were not capable of doing it, that it had to do time domain. So since then, I've been pushing every student to do a time domain. But I think David was able to get the steady state for most complicated cases. So he convinced me that the steady state and the transient will give him the same answer thermally. And then since then, it's been about a year or so, I trust steady state simulations thermal, but I didn't in the past. So some of these things were done longer than a year ago, then transients were done. Some others, we just do the steady state.
Yeah, and it is advantageous to do steady state, stationary solver. If the customer or anybody is interested in steady state, and if it's not necessary to do time dependent, then don't do time dependent, right? If steady state is all that is required,
Look what it says there. It took almost 2 hours, 1 hour and 38 minutes to run.
yeah, but compared to
Yeah.
time
But
dependent.
but in the transient, it takes 2 weeks. Yeah.
So,
Yeah, I can take, no, I mean, not exactly, because, not exactly. If we use the correct laminar flow physics, it should not take 2 weeks. But that was one of the problems that we had, right? We were using a laminar flow solver when we should have used turbulent flow, because, right, we should have checked and not assumed the fluid flow, right? Yeah, because if you use the wrong solver, it's gonna take 2 weeks, 3 weeks, and it may never solve, right? But time dependent, in this case, right, instead of an hour and 38 minutes, time dependent can take maybe 6 hours, it could take a day, 2 days, something like that. If you could do stationary, and that's all that's needed, and nothing else needed, then do stationary. But to do stationary, there's a few things you need to. It's good to know, like, to have an idea of what the steady state solution is going to be, right? Because we could apply like a guess of what those values are, and if we guess close to the actual value, then it's going to converge easily. If we start the model from ambient temperature, then we're forcing the solver to try to solve the model with no help, like starting from ambient, right? But if we give it an initial value that, like a good educated guess, and it's close, reasonable, then you could solve quicker. But that's the only thermal, that's electromagnetics as well, right?
All right.
so I'm sorry,
Yeah.
I have a follow-up question. So, for the previous, the case you showed us, you showed it like for 40 years. So for that case, so, you just said the time step really large to simulate for the 40 years, or?
Well, for 40 years, I just need to I use a time step of about a fraction of a year, like 0.025 years. So I divide by
Okay.
almost divided by 50 or 40, something like that.
Okay.
Typically divided by 50. So 1 year divided by 50, right?
Okay.
Even though the cables are in air in the tunnel, right? The transited air is completed like very fast. The transits in the soul, the slow transits is what dominates.
Okay.
And
thank you.
yeah, and in the case with like time dependent simulation of cables in air, where there's a fast transient, the relative tolerance that you set determines the time step, right? So the lower the relative tolerance, the better the solver would automatically adjust the time step to capture those initial fast transients. So you don't need to like manually try to like force time step. The solver adjusts itself. You know, depending on the solver, we have automatic Newton, constant Newton, right? Damping factor, which we call the deceleration factor. So once the fast transients passes, then the solver will use bigger time steps. I mean, yeah, it'll converge quicker.
Okay.
Initially, it'll be very slow, like very slow. And then once we pass the knee, then it'll speed up.
Okay. Yeah. Okay. Thank you. Yeah.
Any other questions?
Okay. I think we're fine, David.
One last thing is that in the laminar flow, because we have air going in and out and we're forcing the air, instead of open boundary, I use inlet and outlet. Because remember cable in air, the air is being heated and the fluid flow is from moving from top to bottom, right? Open boundary. In this case, we're forcing the air. So I use inlet and outlet, and then I'm choosing normal inflow velocity and outlet pressure condition. So we have different options for this, but there is a difference. When we have forced ventilation, we use inlet outlet. Natural convection, open if it's open boundary, we use open boundary. And that's it. Everything else is the same, pretty much. All right, folks.
All right. Thank you, David.
No problem. My pleasure.
All right. So practical things for the rest for the group. I don't have more material to cover in the class. If there are anything that you guys want us to, I can continue for a few more weeks. In any case, for the people in Mexico who don't know, we are already in the summer, and here the summer activities are very relaxed for the next 2 months, 3 months. We are not completely off, especially those who work in research, but we take it slowly. At least the students can take it slowly. So, are there any other topics that you're interested in? So, if not, this could be the last session, formal session. We could have meetings for this transformer project that we're having. So see how hopefully you
Yes.
can run.
Right
Hopefully you
now,
can.
I changed something in the module and it's running right now. It's been running for. Wait a second, let me check.
You're
It's been running
this
for 1.5 hours. It's running right
Uh-huh.
now. Yes.
So, so should we continue meeting regularly, or should we just meet when it's needed? And I'm talking particularly to the Mexicans, because here we're going to continue meeting regularly, at least once a week in here until we all start traveling. Yeah. In particular, I'm going to be in Mexico from June 11th to the 18th in Mexico City. So I have still about a month now, two more weeks, right? Three more weeks. Yeah. So let me ask directly, Fermin.
Yes, Professor.
What do you think?
Well, I think we can, if you agree, we can plan sessions regularly, maybe once a week or 2 weeks, and in 2 weeks, because we have several projects and we want to show
Okay,
you
so why don't we do this?
opinion.
Why don't we do this? Next Tuesday, we meet at the same time, but there will
Okay.
be no formal presentation. We meet to discuss how we can cooperate.
Okay.
Okay.
Yeah, sure.
So hopefully see how by then has the results, or maybe we have other things. So in 2 weeks, we meet at the same time just to talk, right? And exchange information.
Yeah,
Fayaski
sure.
is very eager to do something, but he's not speaking.
Yeah, if you want, we can ask my students to present something of what they are doing and
Okay, that
short
would be good. That would
presentation,
be good.
10, 15 minutes.
Yeah, and see how we can cooperate because
Sure, Professor.
we
can-
have here good resources for doing things and if you have interesting projects that we can do, well, we gladly work with you guys.
Yeah, well, thank you. Yeah, we will
So let's
take
meet
your
next
offer.
Tuesday at the same time
Okay,
with you guys in command. You will tell us what you want to do, what we want to do, and we'll take it from there.
sure,
But
Professor.
we will stop these formal presentations and these things, okay, and turn it now into a exploration of cooperation.
Thank you.
Okay.
All right,
Okay,
take care,
thank you.
everyone.
David?
Yeah, I said, take care, everyone. So
Yeah.
I won't be
Thank
joining
you,
you, right?
David.
The last session, right?
Yeah. Okay.
Okay, you wanna connect on LinkedIn, you can find me on LinkedIn.
Well, you can find David with ANSYS. He has hundreds of videos using ANSYS for electromagnetics. Okay.
All right.
So Fermin, we meet next time. Oh, there you are. You are in what building are you? You're muted. You're muted. Fermin, you're muted.
You can unmute him.
He's in building C.
Building C. Zeta C. Oh. So it's not where my office was, huh? My office was in Zeta
Yes.
5.
Zeta
Yeah.
4, I think he's there.
I was in Zeta 5 for a good number of years. Okay.
He's still talking.
He's still talking. We can hear him.
Sorry. I am in the office where Professor Leszek used to be. Tadeusz, sorry.
Uh-huh. I see.
This is my office now.
But this is Zeta what?
4.
Oh, no. We were in Zeta 5. Zeta,
No,
no,
where I come here, you were here in this building.
Zeta 4?
Yeah.
Yes, when you were chief of the
When,
graduate
yeah.
Yeah.
When I was there,
section.
the boss?
Yeah, when you were
Yes.
the boss. We were your
Well,
students.
yeah. Anyways, don't tell me how old I am, right?
How are you changing, no?
Yeah, well, I am. I'm aging. There is
Yeah.
one good thing. I'm aging with no aches and pains. I don't have any ache or pain,
Very
or
good. Yeah,
and
I
don't have any
I'm
medicine.
happy to know that, Professor.
Just up to now. But
No,
things can change very quickly at my
yeah,
age.
hopefully not. Very good.
Is that you have transferred your ache and pain to your students.
Uh-huh.
Yes.
Ache campaign. I transfer ache campaigns to Fayad.
Just don't start practicing jujitsu. You'll be all right.
No, David. Yeah. I don't get into those things. Yeah. Okay. So see you
Let's
guys
see
next
you.
week at
See you.
at 1 our time. I think it's 11.
Yes, at the same hour. Yeah, please.
Yeah.
Okay.
All right.
Thank you. Bye.
All right, take care.
See
Bye.
you.
Right.